First, I'd like to go to the syllabus. I meant to send out an email on this, but didn't have time. I believe the Chapter 10 notes are extensively updated, so you might want to download them for today. The Chapter 8 assignment, that should be a 9. In other words, I've put the next assignment up for Chapter 9. Let me see if that actually is it. No, it isn't. But it will be soon. I think it's up there. Should be up there. That should be a 2, and this should be a 9. Let's see if this works. Yeah, there's the Chapter 9 assignment. And it says Chapter 9. So the lectures are up, of course, for last week. Chapter 10 notes have been updated, and the Chapter 9 assignment is there. Now, the Chapter 8 assignment will be due this Wednesday by close of day, meaning before midnight, for Chapter 8. And so whenever you want to start on Chapter 9, we've already covered it, and we're actually into 10. The assignments, the chapters are going to go more quickly for 8, 9, 10, and 11, and then Chapter 12 is a really long chapter. Not sure why that's happening. Whenever that happens, you can always force quit. That's actually a Unix kill command. There's a command in Unix for kill, which will kill any running process. What I'd like to do now is to go back into Chapter 9 in our studio. So I've got to make some changes here. So if we go into 512 in the notes, and I'm going to bring up Chapter 10, the .rmd file. I'm going to go ahead and knit it so we can sort of see where we've been and where we're going to go. So last time we've been talking about the one-way analysis of variance, which we could also call the completely randomized design in general. Well, that's not in general. It actually depends on how you do the randomization. If you randomize the treatment to the experimental units, then it's called a completely randomized design. So last time we went through how to construct the one-way analysis of variance table. And starting fairly soon in section 2, I have added some things, so I want to go back and talk about those a little bit. Now suppose, so let's go back and actually step through these. And I think I'm going to need early on, I'm looking for the R code. Yeah, I need to redo this. So I'm going to read the sols data, a text file in, and again, those are the first. Is anyone having trouble with this? It's happening again. Okay. What now? Can you download? Okay. Can you download that file?
I mean, I can't get on Mountain Air. I don't have any network access right now.
So you can't download the file?
I mean, I have sols.txt.
What now?
I have sols.txt and I have the old version.
Yeah, but you don't have the new versions. So none of you can get on?
I got on.
What now?
I got on
Okay. What, Mountain Air, or did you get on another network?
the network.
What now?
The network.
Mountain Air?
Oh, yeah.
So you're on Mountain Air? Is anyone else on Mountain Air? Yeah. Who isn't on Mountain Air? Who is not on? Try again, see if you can get on. At any rate, it appears that I'm not being allowed to run this command. So I'm going to have to do it locally. Let me call Steve. Got to figure out why this is happening.
Looks like it's not on working directory.
What now?
Looks like it's not on working directory. It's in 523.
Oh, maybe that's the problem. I didn't switch. Let's see. Set as working directory. Okay, let's try this now. Yeah, okay, great, thanks. R is not forgiving if you don't set things up right. It doesn't find things. I wanted to talk about how you might compute the means. We have, if you look at the data set, we have 4 different models, and there are 5 observations per model. And so it's actually, yeah, he's calling me back. Hey, Steve. Yeah, I thought I was having a problem, but it's okay. In our studio, but it's okay. So, I said I thought I was having a problem in our studio, but it's okay. Okay. Okay, thanks. Okay, bye-bye. Bye-bye. So we have model, which is factor, or at least it's converted to a factor, and then we have angle. So you might ask the question, how do I get the means for every factor level? There are several ways to do this. One way is to use, there's a group of functions called apply functions. And for example, if you have a matrix that's all numeric, you can either get the row means or the column means by using the apply function. You tell the object, and then you tell whether you want the rows or the column, that is the margin, whether you want a 1 or a 2, and then you give the function. But tapply, it's actually often called jagged because suppose that you want the means for each model, and suppose the number of observations for each model type were different, which it could be. In the next example, we do have different number of observations in each factor level. That doesn't really matter with tapply. With tapply, the variable I want the means of, in this case I want means, and I want it by the model. So I'm going to apply means to it, and if I do that, those are the means, 33, 43, 49, and 31. Now, there are other ways, as I mentioned, that we can do this. But that's one of the simplest. Now, I could have done it using the by statement, but I'm going to use the by statement. And this is like, if you know SAS or JUMP, there's the concept of a by statement. We do analysis by group. And in fact, there can be more than one group in JUMP and SAS. So suppose I want a 5-number summary for each model type for angle. So I can do that. And if I do it, you see what I get now is for model A, it gives me 5 numbers. Does anyone want to guess what those 5 numbers are? This is a function in R called FiveNumber. And it actually gives the minimum, the lower quartile, the median, the upper quartile, and the maximum. That's called the 5-number summary. And it's very useful because it's the basis for one of the types of box plots you can do. So 5-number, that's been very useful. So that summarizes it for each of the 4 models. And you can see that there appear to be differences. But if you wanted to visualize these differences, it's easier to plot it. And so if I plot it, I don't know why this happens, but somehow I've got to check the default. So let's go over here and look. So it works okay when you do the HTML command to create an HTML file from R Markdown. If you look at that, if you look at, for example, A, which is the one on the left, you can see that the 17 is the bottom, which is the min. The next horizontal line is the lower quartile, which is 24. Then the next one that's a bit more solid is the median, which is 39. And then you can see 42 is the upper quartile and the maximum is 43. So this particular form of the box plot just graphs the 5-number summaries. Now there's another form of the box plot that actually looks for outliers. So this particular form just gives the 5-number summaries, and it's a nice representation. And we can see that certainly the centers of the distribution appear to be different. It's sort of stepping up until you get to D, and then it drops way down. And we saw that with the means. When we looked at the means and the medians are not necessarily the same, of course. And you can see they're not quite the same. If you look at this column right here, these are the medians, and then here are the means. So you can see the means and the medians differ somewhat, not a lot in this case. The medians, of course, are defined that you have 50% on each side. That's sort of a vague definition. There's a more precise way of viewing it. I mean, the problem is, if you have 8 observations, the middle observation is not the 4th or the 5th, and typically by convention we average them. On the other hand, if there's an odd number, like 7, then there is a middle observation. It's also the case that it might be, notice that for say the second group, for example, the median is 44, the but the mean is 43, and that's because there's a slight amount of skewness. So this is a nice this is something that you should probably always do, is visualize your data. And we could do histograms, but we don't have a lot of observations. We only have 5 in each group. And if we did 5, we could do 5 histograms, but with 5 observations, it's not going to tell you a whole lot. This is much better to do the side-by-side box plot. It gives you a representation of what the data looks like. And you can see it's a lot better than the 5-number summary. I mean, you can sort of tell what the differences are by looking at it, but it's not nearly as clear as the graphical representation. So what I want to do now, I've sort of changed things a bit. I fit the default model using the same method as is in the book. And that means that the sum of the alpha sub I equals 0. So we define the alpha sub I as this deviation. If I define mu dot or mu as kind of the grand mean, which is the average of the mu sub i's, and the mu's are the parameters, not the statistics. The statistics are based on data. The parameters are unknown. They're a characteristic of the population. So what I'm going to do here is I've sort of changed the notes so that this conforms with the book. And then later on, I talk about what R does. And I'm going to show you a bit more about what distinguishes the two approaches. So I'm going to run the LM function, and the model is angle tilde model. This kind of model is, in fact, the factor representing the different types of sols. And there are 4 of them, as I mentioned. But I'm going to define my own contrast to be the CONTR dot sum. Now, there's some built-in contrast, such as that. Now, in R, it actually turns out that you could define your own contrast if you wanted to. And so, but there's a built-in one called CONTR dot sum, and that's the equivalent of selecting the sum of the alpha sub I equals 0. Now, sum of the alpha sub I equals 0 automatically comes into play from the way we define mu naught, and then mu sub I minus mu dot is in fact alpha sub I, and with a little bit of algebra, you can see by definition that the sum of the alpha sub i's must be 0. So if I run this model, so I've run the model, and then if you just print the model itself, you get, the only thing you get are the coefficients. If I just print out over here fits sols, now you notice in this particular case there is no model 4, and I'll explain that in a little bit. In other words, there are 4 parameters. There's 39, which is the grand mean, and then these are the deviations. And so you might ask, well, how do you define alpha hat 4, the estimate of the treatment effect for the 4th group? I'll get to that in a minute. What I want to focus on right now is how do you construct the AOV table, and we can construct it using ANOVA. And that gives us the AOV table, which we've looked at before. And we can see that the p-value for testing that mu1 equals mu2 and so forth is 0.038. Now, that's equivalent to testing that alpha 1 equals that all the alphas are 0. Now, if you look at my notes, you'll see that. So we reject the null hypothesis, and we conclude there are some differences. Now, the problem is this particular example is a very nice problem because we design an experiment. We pick 4 sols from each type of sol. We didn't have to reject any sols for whatever reason. We have no missing values. We have what is called a balanced design. Now, a balanced design is nice if it's possible, but a lot of times it's not. I'll give some examples. A lot of times you don't have any control over the sample size because you really didn't randomly select from each group. Sometimes you get patients with different disorders, for example, as the next example will show, and if you're at a particular clinic, let's say, you take what you get. So there's an unpredictable, if you have various disorders, you're not necessarily going to have the same number. Now you could, if you're in a very large hospital, you could randomly select from the group with type A and the group with type B and so forth, so that it is random. But if you do that, you've got to be a little bit careful because the population that you're sampling from, there might be a lot fewer type A's and type B's and so forth. And so there's some subtlety in how we sample and make inferences in this particular case. So there are a lot of examples, where this could occur. And so we're going to look, they give, the book gives a number of different cases in which reasons why you may not have equal sample sizes in each group. So, whether you're looking at botany or wildlife or whatever, and a lot of times you have what are called observational studies in which you get what you get, and there's nothing to assure you that the sample sizes will be equal in each group. So we have an example. We have a psychologist, and you're looking at certain behavioral characteristics, and there are 7 of these, let's say 7 types of behavioral characteristics, and the researcher thinks perhaps that the IQs may differ among these groups. And so, in other words, the IQ of the students in the disorder, there's perhaps some relationship between the disorder and a particular IQ. And so that's, the hypothesis is that there are no differences. That will be the null hypothesis, and the alternative hypothesis, which we often call the research hypothesis, because it's really what you're interested in. I mean, you're hypothesizing that there is a difference, and you probably have some theory about why you think there would be a difference. So the alternative hypothesis is usually called the research hypothesis. So if we read in the disorder data, and I've added quite a bit of text to this from what I had previously. And so if I read it in, and then, since I'm not particularly worried about space, in this case there are 23 observations, and you can see that the sample sizes, the disorder is actually numeric, so I have to be a little bit careful here. First of all, I'm going to attach this I'm going to attach the data frame in the search path, and then I'm going to convert type to a factor, and here are the first 5. Now, having done that, you might want to know how many observations are in each of these types, and of course length is a function, so I can use the t-apply to find out how many observations are in each type. So if I run this particular function, you can see that I have length. I'm getting the length, or the number of IQs in each type. And you can see the first group has 4, the second one has 3, the third has 5, and so forth. The labels are 1, 2, 3, 4, 5, 6, 7. Now, I don't recommend that you use 1, 2, 3. I don't recommend you do that because, it gets confusing when you start labeling things, and then you have to make sure that you remember to convert it to a factor. Otherwise, you don't do analysis of variance, you do a regression. In other words, if I would look at IQ tilde type, and type is 1 to 7, and I didn't make it into a factor, it would do a one-way, it would do a simple linear regression. So you have to remember, I just don't recommend that you label the levels of a factor, 1 to 3, and so forth. It can get confusing, but people do it, so if they do it, just make sure you convert it to a factor, or you will not get an analysis of variance. And it will treat it as an increasing order, as it's like 7 is a more serious disorder than 1. But we don't know what these are. We could perhaps go read about it if there's an article on it. Perhaps it is true that as you go 1 to 7, the disorder is increasing, but we don't know that. And that would still be ordinal, not numeric. We can have an ordered class, that is where, or what we call an ordered factor, where increasing levels really do mean increasing on some scale, even though it's not a numeric scale. Okay, so we see that it's pretty unbalanced. So let's fit this orders now. And the book shows you how to compute this by hand. And so you're always welcome to do this by hand. So you can compute the one-way, both balanced and unbalanced. It starts becoming a little bit harder when it's unbalanced, but the one-way analysis of variance and simple regression and the two-sample t-test, these are all things you can compute by hand. But this is about as far as you want to go when you talk about computing things by hand. Once you get beyond that, you definitely want to use software to do it. But I would argue that even in these simple cases, you might want to do it by hand just to sort of see how it goes once, but you probably don't want to do it twice. Unless I give you summaries, and then the summaries say, okay, I've given you the hard calculations, now compute some things. There's some benefit of doing it by hand, but again, not for too many times. So let's do an ANOVA now. And I'm going to compute the ANOVA. And we can see in this case that the p-value is, it's about, the p-value says what? Well, we can interpret it this way. It's roughly 0.0004, right? So what does that mean? Will you reject? Well, under any reasonable significance level, you would reject, right? Because this would say, if the null hypothesis, could you get something this rare if the null is true? Could you get something, a test statistics, with an F test statistic of 8, it's about 8.149. Could you get that if in fact the null is true? Yeah, you could. It would happen about 4 chances out of 10,000. So, I mean, do you say that the null is true and therefore I had a really rare event? Or is it more likely that the null is not true? Well, when we talk about what's rare, we typically use 0.5, but you could use 0.01 or 0.1, but it's in that range. When you get to 1 in 10,000 or even 1 in 100, it's pretty little doubt that that you should be accepting the null in those cases. That is, we should reject. So we can see that the rejection level, we can see that the rejection level is, well, they have 0, but it's really, you're really, it's basically we're saying it's less than 1 in 10,000. In fact, I mean, the 3 asterisks is 1 in 1,000. It's actually less than that. It's 4 in 10,000. But at any rate, that says that we really seem to have a difference. Now, what I want to talk about now is multiple comparisons. And I want to go through this again. So let's take a look at multiple comparisons. And I've added quite a bit, to this. Now, some of this I don't have some R code in yet. I'll probably keep adding some R code to this. But I was focused on some other things last night, which I'll get to in a little bit. Now, if I'm testing the hypothesis, you might want to do some linear. You might want to test the hypothesis that some C sub I and U sub I equals 0. So, for example, suppose C1 equals 1 and C2 equals minus 1. What would you be testing? If C1 equals 1 and C2 equals minus 1, what are you testing? You're testing that mu1 and then all the other C's are 0. What would you be testing? You'd be testing that mu1 equals mu2. That is, you would be testing that mu1 minus mu2 equals 0. Plus 1 goes with mu1, minus 1 goes with mu2. So you would be testing that mu1 minus mu2 equals 0. That's a sub-hypothesis I could test, right? And that just means mu1 equals mu2. Now suppose I wanted to test that suppose I wanted to test that mu1 is the average of mu2 and mu3. How would I do that? Well, I could do 2 mu1 minus mu2 minus mu3 equals 0, and the rest of the mu's are 0, right? So that would say what? Mu1 is equal to mu2 plus mu3 over 2. And then I could say, well, let's then compare mu2 to mu3. Then I could have 0, 1, minus 1, and then all the rest zeros, and that would test mu2 equals mu3. Now those two, these are called contrast. That's actually why we use C as the coefficient. These are called contrast. And those two contrasts I just defined are what I call orthogonal, but I'll come back to that in a minute. The point is, I could define an arbitrary number of these contrasts. I could define, you give me a set of C values, it works, right? I could define a set of contrast, and I have a t-test for it. You can show that if I look at the sum of the C sub I, y bar sub i's as a numerator, and then the standard error of that numerator is just S sub p times the square root of the sum. That's sum of the C sub I squared. Is that n sub j? It's hard to read. N sub j, I think. It should be n sub j. Or n sub I, I'm sorry. Let's see, this isn't correct. The n should be inside the summation. It should be C sub I squared over n sub I plus, in other words, you sum that up. So I need to correct that. Now, you'll see that down below, what we're doing. The problem with this is that I could do an arbitrary number of these, each testing at the 0.5 level. And if I collectively look at them, I have a high probability of rejecting some of them just by chance, even if the null is true. In other words, I'm not controlling the collection of all these contrasts. So if I have all these contrasts, and I can construct as many as I want, each of which is rejected at the 0.5 significance level, then the probability I reject at least one, even if the null is true, can become fairly large. And so we need some way to sort of, if we have a group of contrasts, we need some way to control the rejection level overall, or what we call the, and I'm going to actually talk about a couple terms. So one of them will be what's called the family-wise error rate. In other words, the error rate for the family of tests we do. So let's look at a couple of these. And what I'm going to do is give some ones that have historically been used. And then I'm going to introduce some new. Let me check something. Oh, okay. I'm going to introduce some new methods. Now consider this. If you are looking at genes, it might be the case that you do an experiment, and this is sort of typical when you're doing genomic type experiments. You may have 20 observations, 10 are controls, and the other 10 are cancer patients. So you have two groups, people with cancer and people without cancer. But you measure, and you're looking for gene signatures. That is, you're looking for markers that might indicate a certain type of cancer. So you do a microarray experiment, and you collect data on maybe 1,000 genes. And in fact, you could do it for far more than 1,000. And then we want to actually test each gene, which would mean we do, if we just did t-tests, that would mean, and we only have two groups, so in principle we could do a two-sample t-test on every gene, and we'd do how many? 1,000. Now the problem is, we'd probably find a lot of genes that are not really marked just by chance because we did 1,000. If we use a 0.05 level of significance, we're going to find some. So here's the problem. We can get very conservative, and we tend to find none, or we can just sort of ignore it and do a bunch of two-sample t-tests, and we find too many. Is there something in between where we're not so conservative and we're not so liberal? Something in between. Well, we'll talk about some strategies that are often used. So I want to talk about, first of all, Fish's OSD. Now, Fish's OSD, first of all, there are a lot of researchers that they'll have a one-way analysis of variance. They don't treat it that way. They do just a bunch of two-sample t-tests. And that's wrong from a number of counts. You have no model. You're just comparing a bunch of groups, but you don't control the error rate. And we have no model, and we have we have a model, but there's dependence among them, because if we compare group 1 to group 2, and we compare group 1 to group 3, those are correlated because they both involve group 1. So we have to be careful when we shouldn't just do a bunch of two-sample t-tests. So what we do is we have a model, y sub ij is equal to mu plus alpha sub I plus epsilon sub ij, and we make certain assumptions about the epsilon sub ij's. And, for example, that they mean zero of variance sigma squared, that doesn't depend on the group, and so forth. We have diagnostics. We can check the model to see if the assumptions, for example, about the epsilons are okay. So we can do all this. And we reject. Then what? Well, then we can do multiple comparisons. And one of the most common, and it looks sort of like you're doing a whole bunch of two-sample t-tests, but there's one critical difference. So suppose we, in fact, do a bunch of t-tests, but the difference is that we use the pooled error term. So we use the error term from all the data, which is the mean square error. In other words, we estimate S sub p. We estimate S sub p by the square root of the mean square error. That estimates what we call sigma hat, which is, in other words, if I say the epsilon sub ij is distributed independently normal of mean 0 and variance sigma squared, we're estimating sigma squared. So we take the square root of it, the standard deviation, I can get an estimate. Well, mean square error estimates sigma squared. We sometimes call that sigma hat squared. And then sigma hat is just the square root of mean square error. So what we're doing here is we're taking the estimate from the complete model. So we're not just doing a bunch of two-sample t-tests that would not pool. Although there is an option for not pooling if you actually look at the if you look at the options. Okay, that's interesting. Now, if I look at the variance of a mean, it's sigma squared over n. So you can think of this as the mean square over n sub I plus, and again, if the two samples are independent, I can add, if I'm getting the variance of a difference or a sum, it's actually the sum of the variances. So I have the mean square error over n sub I plus the mean square error over n sub j. That's where I have an error in that statement up above I have to correct. At any rate, in this case, I can factor out the mean square error. In fact, I can bring it outside the radical if I want and just call it S sub p for pooled. So I do a bunch of t-tests, and the only difference between this and what you might sort of naively do is that I'm using the pooled error term. And then I can reject if that difference is greater than the corresponding t-value with n minus a degrees of freedom. So I can actually perform t-tests and use the critical level with n minus a. Now, if I just did that, the problem is what I call my alpha level would actually be inflated over 0.05, what I call the family error rate. How many, if I have 4 groups, if I have 4 groups, how many possibilities, how many things am I testing? If I test 1 to 2, I'm not testing 2 to 1, it's the same. So if I'm comparing type A with type B, and then A with C, A with D, B with C, B with D, and C with D, how many do I have? Well, I have 4 things taken 2 at a time, right? So I have 4 times 3 over 2, or 6. So I have 6 comparisons. Now the problem is, if I say, well, what is the probability that I reject at least one of those, if I call that the family-wise error rate? Even if I assume independence, it would be greater than 0.05. So this is a problem. So how do I control the family-wise error rate? Well, the way you do it Fish's LSD is very simple. I do the overall F test, which is done at the 05 level, let's say, and if I accept a null, I quit. I don't do multiple comparisons. And if I reject, then I do it. Now, it's that overall F test that really controls the error rate. That's assuming that you have the discipline to not really do it. And the problem is most people don't. You know, they say, okay, here's the F test. Well, it's not quite significant. I'm going to go ahead and run it anyway. And so what happens is people tend to run it anyway, and then if they find differences among the groups, they say, well, there are ways we can do that and be honest about it. And so that's what we want to talk about. So the point is, the way we control the error rate for the whole family, that is all 6 comparisons here, is we control it by the overall F test. Now, I'm not going to talk about student Newman calls other than to mention that if I rank my means, and let me show you the code for doing that. So here, let's say here are the model means right here. Those are the model means. So how do I rank them? Well, there are a few ways to do it. Where do I do it? Sometimes it's hard to find it here. Oh, yeah, I do it down here. Oh, well, before I do this, so how do we do Fish's LSD? There's something called pairwise.t.test. And what you do is the first argument you specify is the outcome variable, and the second argument is the group. The third argument gives the method. And notice there it says p_adjust.method equals none. I didn't adjust the p-values. And so let's do this. Now obviously it would appear to you that there are obviously going to be more conservative ways in this to actually adjust the p-values. So if I adjust the p-values, that is with the Fish's LSD, I don't adjust them. And if I look at this, I want you to look at the output. So I'm doing a pairwise t-test, and I'm looking at the model differences, and I give it this little matrix. So this first element right here, right in here, is comparing A to B, and these are the p-values. So it says if I'm comparing A to B, the p-value is 0.136, which says it's not significant, not even at the 10% level. But are there some differences at the 05 level? Yeah, look at A to C. It's 0.023. So in other words, types A and C tend to be different. Is there anything else that's different? Well, C and D are different, right? So if you look back at the plot, you can see A and C and D are different. So if you look, let's see, the plot's over here someplace. So it's saying A and C are different, and C and D are different. I'm not finding the difference from A to B or from B to C. You can see those differences are less. But there's a pretty big difference from C to D and also from A to C. So that's what we're finding using Fisher's LSD. Are there any questions about what that table represents? It gives all possible pairs. There are 6 numbers here, right? Those are the A to B, A to C, and so forth. Is that clear? Those are the p-values. They're not adjusted. So we just straight ran the t-test. It did pool, and there's a way you can adjust by not pooling, but it did pool in this case by default. Notice that first line. By default, it pools. It says pairwise comparison using t-test with the pooled standard deviation. So by default, it does it, but you can specify that you don't pool. In other words, there's a pool option that's either true or false, and if it's false, it will not pool. It will use the individual standard deviations computed for each 2-sample t-test. So, now student Newman calls, and I'm not going to really do it. In fact, I haven't actually found a method in R that does it. I imagine someone's done it. It's just not a standard method that you'll see. And I just want to mention, the reason I mention it is because it's the procedure, Tukey's procedure, which is the next one I'm going to talk about, extends the student Newman calls. So what I want to look at next is I want to look at the when I ask the question, suppose I wanted to rank the means from smallest to largest. Does anyone know how to do it? Well, it turns out that we can use this rather obtuse way of doing it. That is, I'm saying that I'm looking at the model means, which I had previously computed. In fact, the model means are right up here. So how do I order them? I have to resort the subscripts so that the last subscript becomes the first, and the first subscript becomes the second, and so forth. So how do I do that? Well, let's just take a look at this inner piece right here. What do we get if I use the order function? The order tells the subscripts that I need to have. So it says that if you want them in order, then the first one must be the fourth, and the second one must be the first, and so forth. And so that tells me the order of the subscripts, and then if I use that to subset model means, it gives it in the correct order. Now, the next 2 multiple comparison procedures are based on the idea that if I have 2 means that are close together, that I would expect that I would have, I would be more likely to say they're different than in fact if they were further apart, like D and C. And so it's sort of based on what's called the range. And they have this Q statistics with certain tables in it. And so if you actually look at the student Newman calls, let's see, let's go over here and look. If you actually look at student Newman calls and you look at this Q, that's just sort of like the T we had above. And we had, in the T, we had n minus a, but there's a second parameter here. We have alpha over 2 if we're doing 2-sided. And then before we had, for the T, we just had n minus a. So if there are 4 groups and there are 20 observations, n minus a is 16. So there's 16 degrees of freedom. That was the pooled degrees of freedom. In this case, there's another parameter. There's another parameter called R. I think that's an R. Which tells you the span of the mean. So when I'm comparing D to A, the span is 2. When I'm comparing D to B, the span is 3, and D to C, the span is 4. So the span tells me how far apart they are, and then the bigger the span, the bigger the Q value, so it makes it harder to reject. And so student Newman calls actually gives this for the different spans, which if you look at this matrix, it gives you on the diagonals, and if I look at the next diagonal down and then here, they're doing it by differences that are on the diagonals for the ranked means. So I'm not going to do the student Newman calls. There are tables in the book for it, but again, it's not so commonly used anymore. There's some other methods that are better. But one method that is used a lot is the Tukey's honest significant difference. And what it uses for the Q value is the maximum. In other words, it uses, when R in this case is A, if you have A treatment groups, then A is the maximum span. So for example, if I look here, when I go from 31 to 49, that's a span of 4. So Tukey's uses that maximum. Therefore, Tukey's is more conservative than student Newman Cool's. Now, it controls the family-wise error rate. And so, but it's a more conservative procedure. So as you step it from liberal to more conservative, you have that the Fish's LSD is the most liberal, and then student Newman Cool's gets a bit more conservative, and Tukey gets a bit more conservative. And by conservative, I mean it's harder to reject. You're more likely to conclude the null is true. So we can do Tukey's what's called honest significant difference. Tukey always came up with these clever names. He came up with names like stem and leaf plot, and I think he came up with the name box plot. So he came up with a lot of these names that we use in statistics, and quite a few others actually. Tukey was a very interesting guy. He was at Princeton and Bell Labs, back when Bell Labs was a major force. So there's a function in R called Tukey HSD. Notice the caps. And Tukey's you actually specify it. You actually run the AOV first on the model, and then it takes those results, and it gives the format a little. It doesn't give it in that nice little matrix. It gives it in terms of the actual differences. If you look below, and that's it's called a 95% family-wise confidence intervals. 95% confidence intervals. And so there's B minus A, C minus A, D minus A, and so forth. There are 6 of these. These are the actual differences. And then this is the lower limit. And these are computed based on this Q value and the standard error up here. And so you give the upper and lower limits plus the adjusted p-values. Now, you can actually plot. I saved those results into Tukey difference. You can actually plot it. And notice 0 has a vertical line, and anything that crosses it means it's not significant at the 05 level. So notice none of those 6 are significantly different, although this CD is almost right on. If you look at the p-value, it should be very, very close to 05. You can see that 0.0532, that p-value corresponds to the fact that this almost doesn't include 0. If it doesn't include 0, it means there's a difference. But you can notice, using Tukey's HSD, where were the ones that I found were different? Well, the ones I found different with Fish's were what? A and C and C and D, right? So if you look at A and C, you can see that almost falls out. It almost doesn't include 0, so it's almost significant, but it's not quite. And likewise, the C and D is even closer. So if you look at A and C, that's 0.09. That would actually reject at the 10% level, but not at the 05% level. In fact, neither one of those, as I said, are significant at the 05. So that's a graphical representation, which is actually pretty nice. Okay, so that is Tukey's HSD. Now the next method is Chaffee's. Chaffee's basically lets you do any contrast to your heart's content. Remember that very first way I introduced you, and I said, okay, we could do all kinds of contrasts, and we could test if there's 0, for example. And I said, okay, but we don't control the error rate. Well, it turns out that if you use Chaffee's, you can sort of play around. It gives you an opportunity to sort of search to your heart's content. There's only one problem. It's extremely conservative. It's very hard to reject. So what it does is it uses the actual F value, and then it's using the same types of things, the mean square over 1 over n sub I plus 1 over n sub j. If I'm comparing y sub I with y sub j. But I don't have to do just the pairwise comparisons. I can do any contrast I want, and as many of them as I want to. It's just that you're going to have a tough time actually finding significances because it's so conservative. So it does control the family-wise error rate, but it is extremely conservative. I did want to mention one other thing. Both Tukey's both Tukey's and student Newman Coles require you to have equal sample sizes. Now, as it turns out that you can compute the harmonic mean of the sample sizes and use the harmonic mean as opposed to 1 over n sub I plus 1 over n sub j, which doesn't work with Tukey's or student Newman Coles. You can use the harmonic mean, and if I do that, the harmonic mean, as it turns out, is I have n1, n2 up to n sub a, so I have a of these. So if I take a divided by the reciprocals of each of them, the sum of the reciprocals, 1 over n1 plus 1 over n2 plus and so forth up to plus 1 over n sub a. So if I take a over the sum of the reciprocals of the individual means, that's called the harmonic mean. And it turns out that if you use the harmonic mean, then the student Newman Coles and Tukey's is approximately correct. Now, the only time I would use that if the sample means are almost balanced. In other words, if things are extremely unbalanced, I would not use them. But if things are reasonably well balanced, but not quite, then I think this is valid. But so then again, it turns out that the student Newman Coles and the Tukey's, they're not quite as general as the Chaffe's or the Fish's, and so maybe we can find some other methods that don't require equal sample sizes that sort of fill that middle gap. In other words, if you think of it going from very, very liberal to very conservative, and if you think of the very, very liberal as being Fish's and the very, very conservative being Chaffe's, then the student Newman Coles and the Tukey's are sort of in the middle, with Tukey's being more conservative than student Newman Coles. So that gives you a range of tests, and basically those were the procedures that classically became used a lot. But there was a lot of work on this going back some time after these initial methods were developed. And now I'm going to talk about some of these other methods in 10.6, and I've expanded on what the book does. The book talks about Bonferroni, and I talk about a bunch of other ones in addition to Bonferroni that are sort of in the same family. But that's in section 6, so I'm going to go back up to 4 with 1 degree of freedom contrast, and I just want to define a couple things. A lot of times, and the book actually shows you how to compute some of these. A lot of time, and I don't have any R code. I'm going to have to add that at some point. A lot of times, I have a contrast. Let's call it L, which is A1 mu1 plus A2 mu2, and so forth. And then I have M, which is B1 B1 mu1 plus B2 mu2, and so forth. Those are two contrasts, assuming that the sum of the A sub i's and the sum of the B sub i's both equal 0. So in other words, if the sum of the A sub i's equals 0, the sum of the B sub i's equals 0. Those two L and M are called contrast. Now, if in fact the sum of the A sub I, B sub i's, the cross products of the A's and B's sum to 0, then we say that it's an orthogonal contrast. Now, what we often do, if for example, we have our saw example where we had 4 levels, right? We had A, B, C, and D. And so how many degrees of freedom are there for testing that treatment effect? Is it A? How many degrees of freedom? Remember? In the AOV table. How many does it say? It's A minus 1. Not A. We'll sort of see why in a little bit. I don't know if I'll get to it today, but I'm actually sort of going into, I'm going into some reasons. I said that there's a constraint. You have to put a constraint on the system. The sum of the alpha sub i's equals 0, or perhaps R uses a constraint alpha 1 equals 0. So the question is why do I need that constraint? I'm going to show you in much more detail why you need that constraint, which again goes beyond what the book does, but R allows us to do this. So I can define orthogonal contrast. How many can I define? Well, it turns out if I take a factor like if I take a factor like type, the type of sol, or the model, I guess is what they're using. The model is sol. There are 4 of them, and therefore I have 3 degrees of freedom. I can define 3 orthogonal contrasts, and they will be independent of each other. And so a lot of times we'll break down a factor into orthogonal contrast. And there are certain types of contrast that we often use. For example, we often use, if there's some order, if the levels are like, they're actually quantitative, like 10, 15, and 20. So, and they really mean increasing amounts of, say, some chemical, 10, 15, and 20. I can do what are called orthogonal I can do orthogonal polynomials. So I can fit a linear and a quadratic. I can fit 2 orthogonal contrasts, and I can do it in such a way that one defines a linear relationship and one defines a quadratic relationship. So there are what are called orthogonal polynomials. Those are special cases of these orthogonal contrasts. So if this is true, then I can break the sum of squares. If I look at this term right here, I can take the sum of squares of A and break it into the sum of squares for each of these contrasts. And so how do I compute the sum of squares for the ith contrast? Well, that formula is given down here. The sum of squares for the ith contrast is given if T sub j is the total for the ith contrast, then I can take the sum of C sub ij T sub j, square that, and divide it by n times the sum over j of C sub ij squared. I could also write it in terms of the means in this way. So what I can do is take the sum of squares due to a factor and break it up into individual pieces such that the individual sum of squares add up to the total sum of squares for that factor. And then I can test with an F test. I can test with an F test with 1 degree of freedom for each of these contrasts. The mean square for that contrast over the mean square of error. And so how you do that with actual computations is given in the book. I don't have the corresponding R code yet. At some point I'll do that. Now if you're using JUMP, it actually lets you define orthogonal contrasts if you know how to choose the C's, sort of by this point-and-click method. I'm going to probably show you, as we go along, how you would do these things in JUMP. I can do it pretty quickly, because JUMP is nice in that you can do things quickly. It's not so nice in that you're limited in what you can do. So it's this trade-off between easy use and sort of functionality. I feel that it's more important to have a tool which also allows you to do reproducible research. Now I've been doing reproducible research using RM Markdown, but you can also use SWeave to do it in LaTeX. And there are actually even ways that you can do this using Microsoft Word, believe it or not. Okay, are there any questions? Let's see how we're going. Okay, a few more minutes. So I wanted to start talking about estimation. So I'm going to quickly just do a few things, and then we'll come back to them. We'll start here next time. You have a model, mu plus alpha sub I plus epsilon sub ij, and in particular I'm interested in how do I estimate the parameters, that is, how do I estimate mu, how do I estimate the alpha sub i's, and so forth. Well, mu is the way we define it with the particular constraints we have, mu is the grand mean, so it's y bar, it's the mean of everything. And what about mu sub I, which is equal to mu plus alpha sub I? That's simply the mean of the ith group, which is y bar I. So mu sub I is estimated by mu sub I. And on the right here, they give the standard errors. So the standard error of mu is the mean square error over capital N. Now capital N is the sum of the n sub i's. It's the total number of observations. And then the standard error for y bar I is equal to the mean square error over n sub I. And then I take the square root to get the standard error. What about if I take a difference? What does the difference estimate? Y bar I minus, y bar I minus y bar, not y bar j, but just that. That estimates alpha sub I. And that's a little more complicated. That's the mean square error over times n minus the n sub I divided by n sub I times capital N. And so this, I'm going to show you that calculation I do below. So that estimates the alpha sub I. And how do I estimate alpha sub I minus alpha sub I prime? There's a prime on this second subscript. Mu sub I minus mu sub I prime, and that equals alpha sub I minus alpha sub I prime is just estimated by the mean difference. And that's the key thing we're usually after, is those mean differences, or some other contrast. And that's simply, we've seen this before in the up above, that's simply the square root of the mean square error times 1 over n sub I plus 1 over n sub j. And that's what we've been using, up above, for example, with fishes right here. So that's been a key focus, and that's the thing we're most interested in, are these types of contrast. But I can have a more general type of contrast, the sum of the alpha sub I and mu sub I with the sum of the alpha sub I is equal to 0. And that's estimated by just the sum of the alpha sub I minus y bar sub i's. And then this actually gives the correct formula. That's mean square error times the sum of the a sub I squares, a squared sub I over n sub I. That's the formula that I should have above that I'll correct. So these are the things we're interested in. So if I do a model, if I do a summary of solved fits, it actually gives a summary based on single degree of freedom contrast. In other words, the summary will give a summary of the model object based upon single degrees of freedom. And so there are 4 degrees of freedom. There's a minus 1, which is 3, plus there's the intercept. And so this may be confusing, and hopefully we'll clear this up, but these are the 4 estimates for these 4 parameters. And that's an estimate for mu, and then that's alpha hat 1, alpha hat 2, and alpha hat 3. Now you notice there is no estimate for alpha hat 4, but you can still get it, because if the sum of the alpha sub i's is 0, then alpha hat 4 is equal minus the sum of the other alphas. So you can get alpha hat 4, it's just that the output doesn't give it. So what we're getting here corresponds to mu, and then it's giving the alpha sub i's for the first a minus 1 of them. Now I just said, here I'm just saying, well, what are the attributes of fit? I created something, I have something called fit sols, which is the fitted object, but then I also have something called sum sols, which is the summary object. In other words, summary creates another object. And I just named it sum object. So I named this sum objects the name of the summary when I apply summary to the fitted object. And so what are the attributes of fit sols and sum sols? I want the attributes, because these are things that I can extract from it. And you can see that I could extract the coefficients, the residuals, the fitted values. From the fitted object, I can get all those things. But there's one thing that I can't get from it. You notice that if I'm looking at this particular thing, I have something here called the residual standard error, which is sigma squared hat. You cannot get that from the fitted object. You have to get it from the summary object. And that is given, where is it? Down here. It's given by sigma. In other words, if I want sigma hat, I cannot get it from fit sols. I have to get it from the summary object. Okay? So I'm just pointing out that if you want to extract certain things, you cannot always get them from the fitted object. You may get it from some other created object, which in this case is a summary object. We're here to model means again, and here I can use the dollar sign to extract these attributes. So if I have notice I have fit sols dollar sign COEF. I can abbreviate as long as it's unique. That extracts the coefficients. Now notice the coefficients I'm extracting. The 39, the minus 6, the 4, and the 10 are exactly this first column. So I extracted the coefficients. Now I can extract, for example, the y-hats, the fitted values. I can get y minus y-hats, the residuals. And so I can get the degrees of freedom of the residuals, which in this case will be 16. I can actually get the r squared, and the r squared actually is computed in the book, but I don't have it in my notes. But if you wanted to extract the r squared, and we'll talk about that a little bit more next time, we can do that with the r dot squared. It is computed in the book. Okay. So this, for example, is sigma hat. Notice the 10.06. Where is that above? Well, it's right here. It's abbreviated to 10.1 or rounded off, but that's sigma hat. And so you can see that I can extract, here I'm extracting sig, which is abbreviation for sigma right here, but notice that I'm extracting it from the sum sols, not from the fit sols. And then, I can multiply sigma hat times the square root of 15 over n, and that gives me the standard error of what? That gives me a standard error. That's a fitted standard error of what? Notice it's a 3.897, and let's see, what is that? Oh. I'm a mistake there. I have 20 minus 5 over 5 times 20, which is 100. So I should be estimating this alpha sub I. That's not coming out right. Or either I'm looking at something wrong. I'll have to look at that. This is a good place to stop. Okay. So what I'm going to do next time is I'm going to continue on from here, and I'm going to get an object called the model object. I want you to look at the notes and sort of see if you can figure out what I'm doing. These, in other contexts, are called dummy variables. They indicate the group number. So here's group 1. The first observation is group 1. Number 6 is group 2. And number 11 is group 3. Number 11. And then notice the minus ones. That's actually group 4. But remember, the sum of the alpha sub i's equals 0. So what does alpha 4 equal? It can be defined in terms of the other 3. So this is actually what we call the model object, and it's used to actually do the fitting. So we'll start here next time. Any questions?